Hello, this is Ishwin. In this video, I'll be solving paper 4, variant 3, May June 2020, 0625 physics. Starting with question number 1. A. Define acceleration. You can simply write the formula of acceleration over here, which is change in velocity divided by the time taken for that change. B. Figure 1.1 shows two speed time graphs, A and B, and two distance time graphs, C and D. Describe the motion shown by one graph A. So graph A over here has a straight line with a decreasing gradient, which means this is constant deceleration. Graph B over here is increasing acceleration. C is a distance time graph, and this is showing deceleration. Graph D is it shows constant speed. 2. A scientist fills a container with seawater. The container has dimensions 30 into 30 into 40 centimeter. The density of the seawater is 1020 kg per meter cube. A. Calculate mass of the seawater in the container. So density is mass over volume, which means mass is equal to density multiplied by volume. We need to have all of the measurements in the same units. So I'll be converting these dimensions into meters, which is 0.3 into 0.3 into 0.4, which gives the volume of the water, and that is 0.036 meter cube. So the mass here is equal to 1020 multiplied by 0.036, and so the mass here is equal to 37 kg. B. Figure 2.1 shows a submarine. The submarine is fully submerged in the sea. 1. The atmospheric pressure is 100 kilopascals, and the total pressure on the surface of the submarine is 500 kilopascals, which means the pressure due to the height of the liquid as well as the atmospheric pressure. Calculate the depth of the top surface of the submarine below the surface of the sea. All right. So pressure in liquids is equal to density into gravity into height, which means the height, which is depth over here, should be equal to pressure divided by density into gravity. But we're not given with the pressure due to the height of the liquid, and we're supposed to be calculating that first, which is equal to 500,000 minus 100,000. Since we don't want pressure due to atmosphere, we only want pressure due to the height of the liquid, and that is 400,000 pascals of pressure, which means height is equal to 400,000 divided by 1020 into 10. And so the depth is equal to 39 meters. 2. A hatch on the top surface of the submarine has an area of 0.62 meters square. Calculate the downward force on the hatch due to the total pressure on the top surface of the submarine. So pressure is equal to force upon area, which means force should be equal to pressure into area. And here we're supposed to be calculating the downward force on hatch due to total pressure, which was 500 kilopascals into the area, which is 0.62. And so the force over here is equal to 3.1 into 10 to the power of 4 newtons. 3. In a double-decker bus, there are two passenger compartments, one above the other. A. Figure 3.1 shows a double-decker bus on a tilted platform. The platform is used to test the stability of the bus. The angle the bus makes with the horizontal is gradually increased until the bus begins to topple to the left. Explain why the bus begins to topple. Every object has a center of mass and a line of action from that center of mass. If this line over here is inside the base of the object is going to be stable. Now when I move this object, when I tilt it upwards and its base has the line of center of mass outside of it, it is more likely to topple over than it was in the initial position, because over here the line of action of center of mass was inside the base, but over here it is falling outside of the base, which means it is more likely to topple over. And similarly, this question has the same answer. Line of action of center of mass of bus falls outside of the base. B. There are 30 passengers in the upper compartment of the bus and 2 passengers in the bottom compartment of the bus. State how this affects the stability of the bus and the reason for this. So, having more passengers in the upper compartment raises the center of mass, and so it makes it more likely that the line of action of center of mass is out of the base of the bus, and that is why its stability decreases. See, a bus is traveling along a straight road. The bus and the driver have a combined mass of 16,000 kg when there are no passengers in it. The bus has 73 passengers. The average mass of each passenger is 65 kg. Calculate the total mass of the bus, the driver, and the 73 passengers. Alright, so the mass of the 73 passengers is 73 into the average mass of every single one, which is 65, which is equal to 4,745. So the total mass is going to be the sum of 4,745 plus the mass of the bus and the driver, which is 1600, which is equal to 20,745. Corrected to two significant figures, the answer is 21,000 kg. 2. The fully loaded bus accelerates uniformly from rest to a speed of 14 meters per second. The time taken to reach a full speed of 14 meters per second is 20 seconds. Calculate the resultant force on the bus during the acceleration. Right. So force is equal to change in momentum divided by the time taken, or mass into acceleration, which is the same thing. So the mass over here, the total mass was 2,745 into the change in velocity, which is from 0 to 14, divided by the time taken is 20 seconds. So the answer is equal to 14,525. Corrected to two significant figures, the answer is 15,000 newtons. 4a. Describe in terms of molecules what happens when a liquid evaporates. So the molecules which evaporate are the molecules which have the most energy, because they can then separate themselves, break the forces, intermolecular forces, and escape from the surface. For that, they gain kinetic energy from all of the molecules in the liquid, and that means when the molecules with highest energy have escaped from the surface, the remaining molecules have lost their kinetic energy, and so the temperature of the liquid decreases. B. Figure 4.1 shows wet clothes drying on a washing line in an outside area. State two changes in the weather that help the wet clothes to dry more quickly. That can be obtained by more wind and higher temperature of the air or the wind. 5a figure 5.1 shows a plastic cup. The cup contains sand, an electric heater, and a thermometer. The power of the heater is 50 volts. The mass of the sand in the cup is 550 grams. The initial temperature of the sand is 20 degrees Celsius. The heater is switched on for 2 minutes. The temperature is recorded until the temperature stops increasing. The highest temperature recorded by the thermometer is 33 degrees Celsius. 1. Calculate the energy supplied by the water. Alright. So energy is equal to power into time, which is given in the question as 50 watts, and time is given in a minute, so we'll convert it to seconds by multiplying it with 60. And so the resultant energy over here is equal to 6,000 joules. To calculate a value for the specific heat capacity of the sand using your answer to A1 and the data in the question. Right. Specific heat capacity is equal to energy divided by mass into change in temperature. So energy, which we calculated earlier, is 6,000 joules. Mass given in the question was 550 grams, which is equal to 0.55 kg of mass. And the change in temperature is from 20 to 33 degrees Celsius, which is a total of 13 degrees Celsius of change in temperature. And so the specific heat capacity is equal to 6,000 divided by 0.55 into 13. And so that is equal to 840 joules per kg degree Celsius. 3. Explain why the specific heat capacity of the sand may be different from the value calculated in A2. So this was the specific heat capacity which we calculated based on the practical over here, which means the actual value, and they're asking why the actual value might be different. So over here, the heat needed, the energy needed to change temperature of the sand over here might be different from the actual energy needed because heat might have been lost to the surroundings, and so the actual value might be less than the value calculated over here. B. On a sunny day, the temperature of the sand on a beach is much higher than the temperature of the sea. Explain why. Alright, since they are in the same place, the beach and the sand, they are the rate of energy supplied to both the sand and the beach are the same. But water has a high specific heat capacity, which means to raise 1 degree Celsius of water and sand, water needs a lot more energy than sand. So if they are supplied with the same energy, the temperature of sand would increase much faster than water, and that is why the temperature of sand is usually higher than the temperature of the sea. C. Draw a labeled diagram to show the structure of a thermocouple thermometer. Right. So we have a voltmeter connected via two wires to two junctions. One of them is a cold junction. The other one is hot junction. So the upper wires over here are iron wires. And this one over here is copper wire. 6a, figure 6.1 shows crests of a sound wave after reflection from a solid surface. On figure 6.1, draw crests of the incident wave. Alright. To draw them, I'll first start by drawing the normal, which should be perpendicular to the border or the solid surface. So here we are. Now I'll start by measuring the angle of reflection, which is the angle between the normal and the reflected wave. Alright, this is 40 degrees over here, which means this was supposed to be 90 degrees. And so this is the angle of reflection, which means angle of reflection is 90 minus 40, which is actually 50 degrees. So 50 degrees, sorry. And that means the angle of incidence should also be 50 degrees. To draw the angle of incidence of 50 degrees, I'll add these 50 degrees to 90 degrees since my initial angle is 90 degrees. And that means a total of 140 degrees, or maybe I'll just draw an angle. So here I have 0. I could draw the angle of incidence by drawing a line which is 40 degrees from the border. Yeah, that's it. So this is the angle which is counting as 40 degrees, and this is not the angle of incidence. The angle of incidence is the angle between the normal and the incident rays, which is 90 minus 40, and that is also equal to 50, which was the angle of reflection as well. B. Tick 4 statements in the list below that are false for sound that is audible to a healthy human ear. The wave is longitudinal. Yes, sound waves are longitudinal, but the wave is not transverse, so I'll mark it since this is wrong. The frequency of the wave is 1 hertz. That is not audible. The frequency is 1000 hertz. Yes, that is audible. However, 1 megahertz is not audible. The wave travels in vacuum, and no, they cannot travel in vacuum since sound waves need a medium to travel. C. State a typical value for the speed of sound in water. This value can be 1500 meters per second. 7. Figure 7.1 shows red light traveling from air into a prism made of diamond. The path of the red light is incomplete. A. The refractive index of diamond is 2.42. Calculate angle x. So angle x over here is the angle of refraction. So here we're not actually given with angle of incidence. Angle of incidence is supposed to be between the incident ray and the normal. Since this is the normal, it's supposed to be perpendicular or have an angle of 90 degrees with the border, which means the angle of incidence over here should be equal to 90 minus the remaining angle, which is 40. So angle of incidence is 50 degrees. Um, the refractive index is sine I, angle of incidence, divided by sine angle of refraction. Since we're supposed to be calculating the angle of refraction, sine R is equal to sine I over the refractive index, which is sine 50 divided by 2.42, which means angle of refraction is sine inverse of 0.32, and so the angle of refraction is 18 degrees. B. Explain the term total internal reflection. It occurs C. The angle y is greater than the critical angle of the diamond. Since y is greater than the critical angle, that means the light over here is going to be reflected, as total internal reflection would occur. On figure 7.1, draw the path of the red light through and out of the prism after A. Alright. So here the light would be reflected with almost the same, it's supposed to be the same angle, but we don't need to have an accurate value because angle of incidence is greater than critical angle. But over here we have a normal. And now it's going to be bending away from the normal because it is traveling from a denser medium to a rarer medium. Yeah, that's more like it. 8a, describe what is meant by an electric field. So we're supposed to be writing the definition of electric field over here. Two, state what is meant by the direction of an electric field. Again, the definition. B. Figure 8.1 shows a polystyrene ball covered with an aluminium paint. With aluminium paint, the polystyrene ball is suspended between two charged metal plates by an insulated thread. The ball oscillates between two charged plates. Explain why the ball oscillates. So it might touch one of the plates first. Supposing that it touches the negative plate first, it gains negative charge because it is covered by aluminium, which is a metal conductor. So electrons would be transferred from negative plate to this ball. So negative and negative would repel. It would be attracted towards this positive one. Once it touches this one, it would then gain positive charge, and so the process would repeat. It moves between these two plates and keeps oscillating. So you can write this explanation either way. I'll start by writing the polystyrene ball over here gaining positive charge. See the current, there is a current of 0.29 amperes in an electrical circuit. Calculate the time taken for a charge of 15 seconds to flow through the electrical circuit. So charge is equal to current into time, which means time is equal to charge divided by current, and that is 15 coulombs divided by 0.29 amperes, and so the time is equal to 52 seconds, which is a rounded figure. 9. Figure 9.1 shows a simple direct current electric motor. The coil rotates about the axis when there is a current in the coil. The coil is connected to the rest of the circuit by the brushes. A1. On figure 9.1, draw a pair of arrows to show which way the coil rotates. Explain the direction you have chosen. So here we're supposed to be using the Fleming's left-hand rule. As you can see, the pointer finger is supposed to be indicating the magnetic field, which is from left to right, north to south, and then the middle finger is supposed to be pointing the direction of conventional current. So it moves from positive terminal to the negative terminal, which means it goes from towards you to away from you. Let me mark it over here. The conventional current is moving away from you, and so that means that is how you should be pointing your fingers. And the thumb over here points the, right, I need to mark it over here as well. This is the conventional current direction. And so if you're considering this a left coil, that would mean the force on this left coil is downward, and that means the coil turns anti-clockwise. So we're supposed to be indicating with arrows. So since the force on this one is supposed to be downwards, I'll draw the arrow anti-clockwise. On figure 9.1, draw an arrow to show the direction in which electrons flow from the coil. Alright, I'll change the color over here so that you can differentiate. The electrons move from the negative terminal to the positive terminal, which is exactly the opposite direction of conventional current. Explain why electrons flow in the direction you have mentioned in A1, because electron and this terminal have the same charge, so they repel each other. Electrons are repelled from this terminal. B. State any difference each of the following changes makes to the rotation of the coil in 9.1. 1. Changing the polarity of the power supply to that shown in figure 9.2. Since the polarity over here changes, the current of the direction of current flowing also changes, and that means the uh, coil turns in opposite direction. 2. Changing the coil to the new coil shown in figure 9.1, which means cutting greater number of magnetic field, and that means the coil turns faster. 3. Using a stronger magnetic field also turns it faster. 10a. A radioactive nucleus of carbon decays to a nucleus of nitrogen by emitting a particle. Complete the nuclide equation and state the name of the particle. So as you can see over here, the mass number does not change. The only change is in atomic number, and it increases by 1, which means this is a beta radiation. And so we have a 0 on the upper line over here. The next answer is -1, and its name is beta particle. B. The radiation detector in a laboratory records a reading of 10 counts per second per minute. There are no radioactive samples in the laboratory. 1. Explain why the radiation detector records a reading and suggest a possible source. So of course this is background radiation. And source can be any source. I'll be writing rocks, radiation in rocks. 2. Carbon-14 has a half-life of 5700 years. There are atoms of carbon-14 in all living organisms. An archaeologist digs up some ancient wood in the same laboratory as in B1, which means the background radiation in here is going to be 10 counts per minute. A sample of this ancient wood gives a reading of 20 counts per minute. An equivalent sample of living wood gives a reading of 80 counts per minute. It is suggested that the age of the ancient sample is 11,400 years. Do a calculation to check whether this suggestion is correct. Alright, so first I'll start by calculating how many half-lives have passed in 11,400 years. And you can do that by dividing 11,400 by 5,700, which means 2. So 2 half-lives have passed between the two this suggested age, and we need to see if that is true. Let's calculate the actual counts over here. We'll subtract 10 from 80, which is 70, because background radiation should not be included in calculation. Similarly over here, 20 minus 10 is 10. So the ancient sample over here is has a count rate of 10 counts per minute, and the equivalent sample, living sample, has 70 counts per minute. So let's see how many lives have passed for the sample to have decreased from 70 to 10. We'll start that by dividing it by 2, because for every half life the amount decreases by half. So the first half life leaves the amount with 35 counts, and then the second half life leaves with 17.2. So the question suggests that the 11,400 years have passed, or in other words, 2 half lives. But as we can see over here, after 2 half lives, the amount is 17.5, which is not equal to 10, as we calculated over here is the amount of the ancient count, which means the suggestion made over here is wrong. So if we add 10 over here, which is the background radiation, we get the answer as 27.5, which is greater than 20, which means the age is greater than 11,400 years. And that's it. We are done with this paper. Thank you for watching.